Hello, I'm Choiwah Chow. Today, João, me, and Mikoláš would like to present our work on an algorithm that works exceedingly well on extracting non-isomorphic models from a large set of models. The goal of our work is to develop a simple finite model enumerator that mathematicians can use to study any algebras they want. Given an abstract algebra, they often want to generate some concrete models to look at, to gain insight, or to test hypotheses. Mathematicians have been doing finite model generations for centuries, long before the computer was invented. There exist many finite model generators, such as Maze 4 that use first-order logic to define algebras. First-order logic is very popular among mathematicians because of its simplicity. For example, to define a semi-group, we only need one first-order logic formula to say that the multiplication is associative. However, the problem is that finite model generators based on first-order logic usually generate many isomorphic models. Now, if two models are isomorphic, then we need only one of them because the second one does not provide any new information. We therefore need to extract the non-isomorphic models from a long list of models, and this is where our new algorithm comes in. Now, a simple example will show the magnitude of the problem we want to solve. Suppose we want to generate all inverse semigroups of order 8. Now, to define inverse semigroup in the first order logic is very simple. We only need 4 simple clauses as shown here. The last one in red is not part of the definition. It is for symmetry breaking, which we will discuss later. For this simple algebra, Maze 4 generates close to 29 million models, but less than 5,000 of them are pairwise non-isomorphic. We need to extract these 4,637 models out of 29 million models, a daunting task. First, let's take a look at what isomorphism means in our context. We will not delve into formal definitions or formal proofs of theorems, but to discuss the intuitive ideas behind the algorithm. Here we show two models A and B as defined by the operation tables. Model A is not identical to Model B, as you can see from the last columns of the operation tables. Model A has 3, 2, 0, 1, and Model B has 3, 0, 1, 2 in their last columns. However, if you apply the permutation cycle 1, 2, that is, swap 1 with 2 in Model B, then you get Model A. In other words, Model A can be obtained from Model B by renaming 1 as 2 and 2 as 1. We say this kind of models are isomorphic to each other. It is clear that Model A carries no more information than Model B and vice versa, so we need only one of them. It is expensive to check that two models are isomorphic. Many algorithms commonly used to check for isomorphism actually try all possible renamings to see if one works. Of course, there are heuristics and other tricks that help speed up the search, but it is often a trial and error process. For this kind of algorithm, it would be faster to check that two models are isomorphic than they are non-isomorphic, because if they are non-isomorphic, you will need to try all possibilities. It is even more expensive. We have a long list of models. As in the worst case, we have to check every pair of them for isomorphism. The time complexity will be quadratic in the number of models. So we need to cut the list of models as short as possible. Let's see how we can do that. At the heart of our filtering algorithm is the invariants, which are properties that are preserved under isomorphism. An example would make this idea clear. Suppose in the operation table of model A, we have 0 times 0 equals to 0. We call this kind of element idempotent. Now, if model A is isomorphic to model B, that is, we can obtain model A by renaming the elements in model B, then we would expect to see an idempotent in B also. If there are no elements in B such that E times E equals to E, then there cannot possibly be any renaming scheme to rename an element in model B to 0 in model A. So the observation is that if A and B do not have the same invariants, then A and B cannot be isomorphic. Furthermore, the number of idempotent elements must be the same in the two models. For example, if model A has two idempotent elements, but model B has only one, then after renaming the element in model B to an idempotent in model A, there's no more idempotent in model B to rename to the other idempotent in model A. It should be intuitively clear that, in general, the number of solutions to first-order logic formulas are invariants. Based on our knowledge of algebras, we designed 10 powerful invariants on binary operations that target different areas of algebraic structures. Here we show the 10 invariants for completeness. We're not going to go into details, but to point out that they are basically the number of solutions to the first-order logic formulas. Here's the algorithm. Given a list of models, for each model, we calculate a vector of 10 invariants for each binary operation for each element. Concatenate the invariant vectors into one combo vector for each element. Note that this step is necessary because there may be multiple binary operations. Then sort the invariant vectors in lexicographical order for ease of comparison later. If two models do not have the same combo invariant vectors, then they cannot possibly be isomorphic to each other. Now comes the divide and conquer algorithm. We use the combo vector as a hash key to put the mutually non-isomorphic models into hash table. That is, models in different buckets will be non-isomorphic to each other. This is the divide step. Next, we can process each bucket or block in the hash map independently, even in parallel. This is the conquer step. There's no need to merge the resulting models. You have seen our algorithm and probably agreed that it was very simple and elegant. The question is, does it work? Well, the answer is a resounding yes, as shown in the experimental results. We ran experiments on 3 algebras. We chose these 3 algebras because they are representative in the algebraic world. We see that our invariants have very high discriminating powers. The second to the last column in the table shows that most of the time the number of non-isomorphic models in a block is close to 1. This is good. Why? Well, if a block has 100 models and they are all isomorphic, then the number of non-isomorphic models in the block is 1. In that case, we only need 99 comparisons to get rid of the 99 isomorphic models. If a block has 100 models and all of them are non-isomorphic, then we will end up comparing every pair of them. That is, we need 100 times 99 divided by 2 comparisons to see that there are 100 non-isomorphic models in the list. The discriminating power is an important factor that determines the efficiency of our algorithm. Now more results. Once we pre-process the models and put them into blocks, we use maze-force isofilters to extract non-isomorphic models from each block. In terms of runtime, we see an improvement of roughly 2 orders of magnitude by our invariant algorithm. For example, for Quendos, which is the bottom 3 rows in the table, it was about 600 times faster with using invariants than without using invariants. For quasi-groups, without using invariants to break down the 11.5 million models into smaller blocks, maze-force isofilter simply cannot handle it. As you can see from the table, a nice property of the invariant algorithm is that it is very scalable. It gives more improvements when the dataset is larger. How about other ways of generating non-isomorphic models? In general, there are 2 approaches. Either we suppress the generation of isomorphic models in the search phase, or we do post-processing to get rid of the isomorphic models in the outputs. Our algorithm falls into the latter category. It is important to note that these 2 approaches are complementary to each other. You don't have to choose one over the other. You can use both. However, most research focuses on suppressing the generation of isomorphic models. They use symmetry breaking algorithms to reduce the number of isomorphic models. The most popular and simple symmetry breaking algorithm is the least number heuristic, and the related extended least number heuristic, XLNH. Many finite model generators such as Maze4, SAM, Falcon, etc. have LNH built into their systems. It is very effective. Now take an example. Remember the inverse semigroups of order 8 we've been talking about? Without using LNH or other symmetry breaking algorithm, Maze4 would generate 120 million models. With LNH, the number cuts down to about 30 millions. With an additional symmetry breaking clause, it is further down to 29 millions. However, LNH and other symmetry breaking algorithms generally do not guarantee that the outputs do not contain isomorphic models. To completely suppress isomorphic models in the search phase is a hard problem that few systems try to do. As far as we know, two systems, SAM-K and SAM-D, try that, but it's either yet to be completed or would leave some isomorphic models in the outputs in some cases for efficiency reasons. If not all isomorphic models are suppressed in the search phase, then we need to do post-processing to get rid of them. Maze4's isofilter and the Loops package do such post-processing, and both use invariants in some limited way. Maze4's isofilter has only one invariant, which can be a problem for some algebras, such as groups and quasi-groups. The Loops packages use 9 invariants that are geared towards the special properties of quasi-groups and are less general than ours. Plus, the Loops package works only for quasi-groups due to the framework it is in. Our algorithm does not have such a limitation. Moreover, neither one of them makes use of hashing to make sure non-isomorphic models never cross paths. This introduces some inefficiency in their algorithms. The results of our research open a whole new line of research into using invariants to eliminate isomorphism in finite model enumeration. We have seen that invariants are good, so why not have more? We are going to have more of them to target different areas of the algebraic structures. We will also extend the algorithm to include invariants on unary operations. As we have more and more invariants, we want to be able to pick a smaller subset dynamically to use for specific algebras. So in summary, the invariant-based algorithm follows the divide and conquer paradigm, uses invariants both as discriminators and as hash keys to separate non-isomorphic models into blocks so that there are no isomorphic models across blocks. Each block can then be processed independently and in parallel, with no extra work needed to combine the results. This algorithm is efficient, scalable, parallelizable, and works well with other systems. That's all I have. Thank you.